All right, thank you all for being here. And we're going to go ahead and get started with number 18, leaving off from where we finished yesterday. All right, so if you're keeping track of where we are in the course, we're getting towards the end of chapter 4. This is actually the last chapter 4 question on the mock exam. And it asks us to use MO theory, molecular orbital theory, to predict the bond order in the C2 2- anion. In most questions, it'll be obvious like this one that we want you to use molecular orbital theory, but I would say in general, if we're asking you a question about the bond order or the number of unpaired electrons in a diatomic molecular anion, something with 2 atoms only in it, then you can be pretty certain we're going to want you to use molecular orbital theory to do that. And the problem that you have on molecular orbital theory on your final exam is going to be sort of a mixture of stuff like this, where we actually ask you to predict a bond order or a number of unpaired electrons. That's probably the most common, but we do have a few conceptual questions sprinkled in, so you want to at least understand some of the basic background of molecular orbital theory as well. So in this question here, we're asked for bond order, and to get the bond order or number of unpaired electrons, you need to first know the ordering of the molecular orbitals that you're considering. So this is carbon, C2 2-, and so for boron, carbon, and nitrogen, we're going to have this ordering of the molecular orbitals. So the lowest energy orbital is always going to be the sigma 2s. So I'm just going to draw the molecular orbitals that result. We should be familiar with the idea that these molecular orbitals form by combining the atomic orbitals. So the 2s orbitals combine to make sigma and sigma star, sigma being the bonding orbital that's lower, sigma star being the anti-bonding orbital that's higher in energy. And then once we get to the 2p orbitals, the molecular orbitals that are derived from 2p, when 2p orbitals combine, they can make a sigma or a pi, depending on whether the p orbitals combine head-to-head or side-to-side. In the boron, carbon, and nitrogen, the first half of the p block, it's the pi 2p that comes first, and then sigma. So the two bonding orbitals, sets of bonding orbitals come first. Degenerate set of pi bonding orbitals, and then sigma. And then the top 2 orbitals in any diagram are always going to be pi star and sigma star from the 2p. All right, so this is the ordering of the orbitals that's appropriate. The other one, just for completeness, would be if you go to the second half of the p block, oxygen, fluorine, or neon, or anything else in those columns. There's one small difference that we should hopefully be aware of by now. So the bottom of the diagram is the same, sigma and sigma star from the 2s. But then where you see a change is in these middle 2 here. So in the second half of the p block, the sigma 2p comes first and then pi, so we switch the ordering of the 2p bonding orbitals, and then the top part is still the same. All right, that is particularly important if you're predicting the number of unpaired electrons. It doesn't matter so much for bond order, because all we're doing is flipping bonding orbitals, and as long as you get the total number of electrons correct, that'll give you the correct bond order. Okay, so we have to figure out how many electrons we have in this. So this is the C2 2- anion. So going quickly to the periodic table, carbon is a group 4 element, so it's going to have 4 valence electrons. These molecular orbital diagrams include all the valence electrons. So each carbon is going to contribute 4 valence electrons. It's a 2- anion, so that's 2 extra. And that's going to give us a total of 10 electrons. All right, so once you know the ordering of the orbitals that you're using, in this case we're going to use the diagram on the left, the important thing then after that is to figure out how many total valence electrons go into there. And you're just going to fill the orbitals from bottom to top, following the same rules we do for atomic orbitals. So for those 10 electrons, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to end up filling the sigma 2p last. And then if we want to calculate the bond order for this, remember that bond order is 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. So every time you put electrons into bonding orbitals, you increase the bond order, and then every time you put them in anti-bonding, you're going to decrease it. So it's bonding minus anti-bonding. So for this particular one, it's going to be 1/2. Bonding orbitals are the ones that don't have stars next to them. They're the ones that would be lower in energy than the atomic orbitals they come from. So we're going to have these 2 electrons that are in sigma 2s, and then 4, 6, 8, 6 more electrons that are in the pi 2p and sigma 2p. So we have a total of 8 bonding electrons, and then only these two, sigma star 2s, are going to be anti-bonding. So it's going to be 8 minus 2 multiplied by half, so we get a bond order of 3 would be the correct one for this. So all of these anti-bonding orbitals from the 2p, the pi star, and the sigma star are empty in this case, so we just have the 2 anti-bonding electrons. 8 plus 2 is 10, that's going to be the total number of electrons, and we're just partitioning them between bonding and anti-bonding. All right, so any questions on this problem or this topic? All right, I think I have notifications enabled, so if you guys send in a message, maybe I already missed one. Do I have the chat window? Someone sent a message. Oh, so the question that came in earlier that I missed, I apologize for that. Will we be able to have a cheat sheet on the final? Yes, the cheat sheet rule that we put into effect during the online portion of the course is going to be there for all the remaining exams, including the final. So it'll still be the same thing, one handwritten page, ideally on the back of your periodic table. So you can use the cheat sheet on the final. And it's sort of up to you to decide which information is most important to include. There's a lot of information that could potentially be useful. So leave it up to you guys how to do that. All right, so that takes us to the end of that one. If there's any other questions, I can circle back in a little bit, but let's move on to number 19. So now we're getting into chapter 5 material. Sorry, I'm going to turn my video off. Sometimes I always forget to do that, and it causes my computer to lag a little bit. All right. The question that also came in that I just saw is which orbitals are non-bonding? This is not letting me receive messages. Hang on a second. That's why I'm not seeing you guys. Available. All right. Now I should see any messages that come in real time, so I won't miss them. But the question that came in was which orbitals are non-bonding? We don't have to worry about that for diatomic molecules. So non-bonding orbitals is something that you will see in more complex molecular geometries, none of which we had to deal with in this course. So if you were to start going to trigonoplanar or tetrahedral or other types of geometries and start doing molecular orbital diagrams for those, they would typically have non-bonding orbitals. But in the types that we're dealing with diatomics, with the one that we just went through being a representative example, none of these orbitals are non-bonding. They're all either bonding or anti-bonding. All right, so on to number 19, which is the beginning of chapter 5, which again dealt with mostly moles and stoichiometry and things of that. The first topic that we covered, and which you'll likely have a question on, is atomic mass. So if we have naturally occurring silver, it has two isotopes, 107 silver, which has this mass, 106.905, and then 109 silver, which has a mass of 108.905. If the atomic mass of silver is 107.87, what is the percent abundance of 107 silver? So if you see a problem like this that is relating isotope masses and atomic masses, there's really one formula to be aware of. It's going to be that the atomic mass, the number that you would read off the periodic table, which is in this case given to us, is going to be the fraction of each isotope multiplied by its mass. So we're going to do for each isotope fraction times mass. And then in this case there's two isotopes, there's going to be a second term, fraction of the second isotope, 109, times its mass. All right, so it's fraction times mass for each available isotope. And this is the only equation that all these problems are going to be sort of based off. And the question is, what are we asking you to solve for? In this case, we're asking you to solve for a percent abundance. So basically the fractions are going to be our unknowns. You could also have to just calculate atomic mass if we gave you all of the percents or fraction abundances and all the masses. In this case, though, the fractions or percentages are unknown. So I'll call that the fraction of 107, I'll call x. The fraction of 109, I'll call y. So we have those two unknowns. And so then putting numbers in, the atomic mass was given as 107.87. And that's going to be equal to the fraction of 107, which is x, as I'll call it, multiplied by its mass. The mass of the 107 isotope is 106.905, plus the fraction of the second isotope, which we called Y, and then the mass of the second isotope is 108.905. All right, so that's our first equation. But we can't solve one equation if it has two unknowns, so the other important relationship that we always use is that the sum of the fractional abundances is going to have to equal 1. Okay, we're doing it in terms of fractions here, so the adding them together should be 1. And that means if we're going to solve for x, that's the one that we're looking for, the percent abundance of the 107 isotope, we can rearrange this and say that y equals 1 minus x, and then we can put this in up here for y. Okay, so what we get is 107.87 is equal to 106.905x plus 108.905. We're going to replace y with 1 minus x. All right, so this is the pretty typical algebra you'll have to do in these types of problems. And then we're going to just solve for x, which is the fractional abundance of the 107 isotope. Now you do want to be careful when you're reporting answers here. Make sure you read the problem closely and look at if we're looking for the fraction or the percent. Here we're looking for the percent abundance, so we're going to get the fraction initially of 0.5175 when we solve the equation above for x. That's the fractional abundance. We want the percent abundance, and so anytime we ask for percent, it's going to be fraction times 100. So I've seen a lot of people every semester I've taught this course, not to pick on you guys, but a lot of people who have made this mistake of reporting the fraction instead of the percent or vice versa. So just make sure you read the problem closely, and if it's asking for a percent, we need to multiply the fraction by 100 to get 51.75%, which is the number that we would actually put in. All right? So do we have any questions on this problem or this topic? It's, again, not a lot of variation. We could either ask you to find the atomic mass if we gave you all of the fractions in the masses, or in this case, the fractional abundance was the unknown. Keep in mind that the relationship of all of the fractional abundances adding together to be 1, or all of the percentages adding to be 100, could certainly be useful in problems like this. Make sure you keep that in mind always. All right, looks like there's no questions coming in, so I'll move on from that one. And we'll go to number 20. All right, so number 20 is a classic mole conversion problem. So we have, in this case, we want to know how many phosphorus atoms are found in 5 grams of calcium phosphate. Take the log and enter your answer to 2 decimal points. So because we're starting with a mass and we want to get into number of atoms, we should recognize right away that we're going to have to find moles as sort of an intermediate calculation to do that. And to do that, we first need to get the chemical formula of the compound. So this is a review of some stuff we talked about yesterday. But if we have calcium phosphate, we can go to the periodic table to figure out what the expected ionic charge is for calcium. This should be an ionic compound because it's a metal, calcium with a nonmetal polyatomic ion. So calcium is in the second column of the periodic table, so we would expect it to form a 2+ cation. So this ionic compound that we're forming, calcium phosphate, is going to be calcium 2+, and then we do have to remember there's no real systematic way of getting this, that phosphate, the formula is PO4 and the charge is 3-. So if these are the two ions that make up the compound, to get the correct chemical formula, we just take the charges and cross them over to make them subscripts, and that leads us to a correct formula of Ca3 and then phosphate PO4 taken twice. So that's the formula of our compound, and now we can start doing the calculation. The other thing that we'll need, though, is if we're going to convert mass to moles like we're going to do in this problem, because we're starting with a mass of calcium phosphate, we're looking for number of atoms, so moles is, as we said, going to be an intermediate. We do need the molar mass. So to review how to calculate molar mass quickly, something we've been doing now for a while over and over again, molar mass is just the sum of the atomic masses in this chemical formula. So we have 3 calciums, and if we go to the periodic table, you would find that the atomic mass of calcium is 40.08. So that's calcium. The formula of this compound has 2 phosphoruses. Each phosphate has 1, and there's a total of 2 of them. So that's going to be 2 times the atomic mass of phosphorus, which is 30.97, All right, sometimes we're nice to you when we give you the molar masses, other times we're not. So we just sort of decide randomly whether to be kind or not, so you just have to be ready for it. So in this case, we're going to calculate the molar mass, and it's going to be 8 oxygen atoms, 4 from each phosphate. 2 phosphates gives us a total of 8 oxygens. The atomic mass of oxygen is 16. And so what we should get is something like 310.18 grams per mole. All right, so that's the molar mass of calcium phosphate, which we're going to need in the first step. So now that we have that, we have all the information we need to go through and do the string of conversions. So let's write down what we're looking for first, which is the number of phosphorus atoms. That are contained in what we're given, which is 5 grams of calcium phosphate. All right, and so then what we do is we're going to first convert this to moles, as we said. So 1 mole of calcium phosphate, and the mass that we just found, the molar mass, is 310.18. All right, so that converts grams into moles. The grams cancel out. And then now that we have moles of calcium phosphate, there's sort of a choice here how we do this. We could either convert this into number of formula units, or we could first convert to moles of phosphorus. It really doesn't matter. I'm going to do it the second way that I described. So if we look at the formula of this compound, there's a total of 2 phosphorus atoms, as we said. We used that up here when we calculated the molar mass. And so we can say that in 1 mole of this compound, we have 2 moles of phosphorus. So that gives us 2 moles of phosphorus, but we're looking again for a number of phosphorus atoms, so there's going to be one more step here in a second. So that gives us moles of phosphorus. And then finally, to get number of phosphorus atoms, once we have moles, we're going to use the definition of a mole, which is Avogadro's number, not to be confused with avocado's number, which is the number of atoms in guacamole. But anyway, it's going to be number of atoms in 1 mole, so we're going to use 6.022 times 10 to the 23rd. That's the number of phosphorus atoms in 1 mole of phosphorus. And so what that comes out to is 1.94 times 10 to the 22nd phosphorus atoms. Typically in Blackboard, there are some questions where we would ask you to enter this in exponential notation using the capital E notation. This one asks for the log of the answer, which we still will do sometimes. So make sure, again, you know how to take the log on your calculator that you're using for the exam, and also follow the instructions closely in Blackboard so that your answer is reported correctly. So we're going to take the log of that number to report the final answer of 22.29. As I've said before in exam reviews, there's no practical reason to take the log other than to make it easier to enter the answer into Blackboard. So make sure you follow those directions closely. It's always a shame to go through all these steps and then just report the answer wrong at the end. So that's how we handled that one. So any questions that you guys have that I can cover now? All right, so nothing came in. Just remember on these problems, the step that is most often forgotten is this one here, to either convert moles of the compound into the moles of atoms, which is what we're looking for, or you could have reversed these steps. We could have first converted moles of calcium phosphate into formula units by multiplying by 6.02 times 10 to the 23rd, but then we would still have to account for the fact that there's 2 phosphorus atoms for every formula unit. So these last 2 steps, multiplying by 2, multiplying by Avogadro's number, can be done in either order, but we do have to remember to do both of them or we won't get the right answer in this problem. All right, so on to 21. In this case, we have an unknown element problem, and as we've seen throughout the semester, there's a few different varieties of problems like this where we're asked to find an unknown element or an unknown compound of some sort. And typically the way we do that is we find its molar mass. And so in this case, we're looking for the identity of the metal M in this chemical formula MCl3. And in most cases, what we want to find is the molar mass, or in this case, the atomic mass, since it's just a single element. So that's what we're going to do to identify what M is. Once we find the atomic mass, we can locate that on the periodic table and match it up. So anytime you want to find an atomic mass or a molar mass in more general terms, if you can find the mass of that substance and the moles and then divide the two, that will give you the molar mass. Remember, molar mass is grams per mole. So if you have both quantities, grams and moles, dividing the two will give you what that molar mass is. So we need to find this for M. We need to find both of them. Now, what we're going to do here to get the grams of the metal is we're going to assume that we have 100 grams of compound, because we're given things here in terms of mass percent. And so if we assume 100 grams of compound of the MCl3, we're told that we have 35.62% chlorine, which means in 100 grams we'd have 35.62 grams of chlorine. And then that means the rest of these 100 grams, or the rest of that 100%, must be the metal M. And so in 100 grams of compound, if we have 35.62 grams of chlorine, we have 100 minus 35.62, which is 64.38 grams of metal. So again, always remember that when we're dealing with mass percents, in this case, or any sort of percentage, the sum of the percentages should equal 100. So if we have 35.62% chlorine, we have 64.38% metal, which means in 100 grams of the compound, we would have 64.38 grams. So that's the mass we're going to use. For a problem like this, we can assume whatever mass of compound we want, but 100 grams is most convenient because we're given the mass percent. The next thing we need to do is find the moles of M that are in this compound. And so to do that, we don't know the identity of M, that's what we're trying to find, but we do know the identity of the other element, chlorine, which is 35.62 grams out of 100, and we know the ratio of metal to chlorine from the chemical formula, M1Cl3. So both of those together can allow us to figure out how many moles we have. So we can first figure out how many moles of chlorine are in 100 grams of compound by taking the mass of chlorine and then dividing by its atomic mass to get to the moles of chlorine. So from the periodic table, the atomic mass of chlorine is 35.45. So now that we have moles of Cl, we can use the chemical formula MCl3. And so we want to convert moles of Cl into moles of metal. So we're going to do it in this way. And the chemical formula tells us that we have 1 mole of metal for every 3 moles of chlorine. This is MCl3. All right, and the subscripts in that formula give us the relative numbers in moles of each element. So this gives us then the moles of metal that are in this, 0.3349. And so we can divide the mass that we had earlier by that number, 0.3349. And what this ends up with is 192.2 grams per mole. And then what we're going to do is go to the periodic table, find that atomic mass, and figure out which element it's closest to. So if we go to the periodic table, we look for 192.2. They're going to be typically in increasing order. And so what we find is that matches up with atomic number 77, which is iridium, which has an atomic mass of 192.2. Now, if you guys have been, sorry, I went to the wrong screen again. If you guys have been vaguely paying attention in this course throughout the semester, I did mention at least once, if not more than once, that iridium IR is my favorite metal. So it's no surprise that that's the answer to this question. So the metal is IR, which is iridium, my favorite in the whole world. Everybody has a favorite element, whether you realize it yet or not. But that's going to be the answer here. Now, as a fair warning, I didn't actually write any of the exam questions, so it would not be a good strategy to just guess iridium for all the exam questions because I didn't write them. But it is my favorite, and it is the answer here for that reason. Okay, so any questions on this problem? All right, moving on then. We're now into, if you're keeping track of where we are, already back into chapter 6, dealing with solutions, reactions, and other things about aqueous solutions. So we want to know if we have the net ionic equation for sodium hydroxide and iron 2 chloride, it contains which of the following species? So in these types of problems, you need to consider both whether the substance appears in that equation at all. So whether, NaCl, Na+, OH-, FeOH2, whether those substances are in the ionic equation, and also what the coefficient is. You'll notice that these some of these have coefficients attached, so we'll need to look at both the coefficient and the substance and figure out should that be in the net ionic equation. So let's go ahead and generate the net ionic equation. So the formula for sodium hydroxide is NaOH. So we're going to start with aqueous sodium hydroxide, and then we're going to start with aqueous iron 2 chloride. So iron 2 chloride tells us that we have a +2 charge on the metal, Fe. Chloride is going to have a -1 charge always, so the formula would be FeCl2. So in a typical reaction, you're going to have two aqueous species as reactants. These are two ionic compounds, so we should anticipate precipitation as being a potential outcome. And then to predict the products, we're just going to switch the cations and the anions with each other. So in one product, we're going to take the cation from NaOH, which is Na+, and we're going to pair it with the anion from the second reactant, which is Cl-. So the first product is going to be NaCl in either order. Doesn't matter which order you write them in. And then the second product, we're going to take Fe2+, which is the cation from this reactant, and we're going to compare it with, we're going to partner it with OH-, which is the anion from NaOH. So the second product is going to be FeOH2. We're going to keep the charge the same on the metal, still +2, which means we need to have two hydroxides, two OH- to balance that. And then for the products, we need to think about whether they're soluble or insoluble to predict whether either or both of them will precipitate. So sodium chloride, we should be very familiar from our everyday life that this is just table salt, very soluble in water, as is anything that has sodium Na+ as the cation. So this is going to be remaining in solution AQ. But then iron hydroxide, most hydroxides are insoluble except for the group 1 metals, lithium, sodium, potassium, and so on, and except for some of the group 2 metals, the heavier ones, calcium, strontium, barium. So basically, transition metal hydroxides like iron are pretty much all insoluble. For our purposes, they're all insoluble. So that's going to form a precipitate, so we're going to mark it with an S to indicate that it comes out of solution as a solid. So this would be what we call the molecular equation or the formula equation, where we're writing things as intact species. We haven't put coefficients in yet, so we should probably do that. So if we have two chlorines on the reactant side, we need 2 in front of NaCl. And now that we have 2 in front of sodium, we also need 2 NaOHs, and that should balance it. So relatively simple coefficients, as is usually the case for these. But that's going to be the balanced molecular equation. But we're looking for an ionic here, so we have to go and sort of do it in 2 more steps. So for the total ionic equation, and you can take some shortcuts here if you get very familiar with this process and get good at this, but the full process, and to help go through all the steps individually, is going to go from molecular first to the total ionic equation. And so for that, we're going to take any species that's soluble with an AQ next to it and divide it up into its individual ions. So the sodium hydroxide is going to divide up into Na+ and OH-, each with a coefficient of 2 that modifies it. And those are both AQ. And then the second reactant, FeCl2, is going to also be divided up into its constituent ions, Fe2+, and then because of the subscript of 2, that's going to make 2 Cl- when it dissolves. And then on the product side, we have NaCl is still aqueous, still dissolved, so it's going to be broken up as well to Na+ and Cl-. And then the second product, though, this is our precipitate, the one that forms as a solid. Because it precipitates, it's not going to be divided up into ions anymore. It's going to be just written as is, FeOH2 solid. So that's our total ionic equation, which includes all of the ionic species written out explicitly. And then for the net ionic equation, which is what we're after in this problem, we have to look at our total ionic equations and cancel out spectator ions. Those are the ions that appear on both sides unchanged in their form. So Na+ is on both sides, so that's going to be crossed out as a spectator. And then Cl- is also a spectator ion appearing on both sides of the arrow. So what we're left with for the net ionic, conventionally writing the cation first, but not necessarily required to do that, is going to be Fe2+ and 2 OH- on the reactant side, and then the precipitate FeOH2 on the product side. All right, and as is usually the case when you have a precipitation reaction like this, the net ionic equation is just whatever 2 ions combine to make the insoluble product. So which of those appear in the net ionic equation? Well, neither of these do, because sodium chloride is soluble, so those are going to be aqueous on both sides, and then all be spectator ions. But we'll notice that 2OH minus appears on the reactant side, FeOH2 solid appears on the product side, so both of these, C and D, will appear in the net ionic equation, so the correct answer would be E, that two of these appear in the net ionic. Okay, do we have any questions on this problem or on the concept of ionic equations? All right, nothing's rolling in, so let's keep moving so we don't keep everybody too long. All right, so that was sort of more of a qualitative or conceptual aspect of aqueous solutions, understanding how different things react in solution and writing out those equations. This one is more quantitative, dealing with molarity. So we want to calculate the molarity of perchlorate in a solution containing 3.58 grams of aluminum perchlorate dissolved in 125 milliliters of solution. All right, so again, for this problem, it's going to be necessary to have the correct formula for the compound. We did give you the molar mass here, this number here with the script M. We usually abbreviate it as MW, but that means molar mass. So that number is given, but we do need to know the formula as well for this compound. All right, so if we want to look at aluminum perchlorate, we need to go again to the periodic table, just like we did before, and figure out the charge of the cation first. Aluminum Al is not the most obvious. It's in group 3, but it is a metal, so it does form cations. And the way that it does that is it's going to lose all 3 of its valence electrons. It's going to lose the 3p as well as the 2 3s electrons. So aluminum loses all 3 of its valence electrons to form a 3+ cation. So that's not the most obvious one, as we said, but it's one that we should know. So it's going to be Al3+ for the cation. And then the anion perchlorate, we have to also remember this formula. We saw a different chlorate yesterday. Perchlorate is ClO4-. So the correct formula for this compound is Al with 3 perchlorates to balance the charge, ClO4-3. All right, and then what we're looking for in this problem is the molarity of perchlorate, the molarity of ClO4-. Remember that the definition of molarity is moles of that specific substance, in this case the perchlorate anion, divided by the liters of solution. All right, so the denominator is more or less given to us because we're told that it's 125 milliliters of solution, which we can easily convert to liters, but we have to calculate moles of perchlorate using a very similar calculation to one we just did a couple of problems ago. So looking for moles of ClO4-, we're told that we're dissolving 3.58 grams of the ionic compound aluminum chlorate. And so our first step is going to be to convert that into moles to get the moles of the compound that we have. And the molar mass that we gave you in this was 325.32 grams per mole. So it's 325.32 grams of that compound in 1 mole. So by dividing by that, we can cancel out grams and get into moles. But this is moles of the whole compound. We're looking for moles of perchlorate. So we again have to remember that last step. If you look at the formula of the compound, there's a subscript of 3 next to perchlorate. So that means we're going to have 3 moles of perchlorate for every 1 mole of compound that we dissolve. All right, and so that gives us the proper number. Again, this very last step, multiplying by 3, is the one that's most often neglected in problems like this. So you have to pay close attention to what we're asking you for the molarity of, whether it's the molarity of the whole compound, or in this case, just the molarity of one of the ions, and make sure that we get how many moles of that specific ion we have. So that's the number of moles, and so we can now put this in. We have 0.0330 moles of the ions, and then as we said, the volume of the solution is 125 milliliters. For molarity, that needs to be converted to liters, so we divide by 1,000, and that's going to be 0.125, just move the decimal place over 3. So 0.0330 moles per liter works out to a molarity of 0.264. So we would just enter in the number 0.264 as Blackboard would instruct us to do. Okay, any questions? Okay, onward and upward. All right, one of our favorite topics from this course, balancing redox equations. We gave you 2 of these on the last exam, or sorry, on the second exam, not the third exam. 2 of these on the second exam, the first one that we had online, and now we're just likely just have 1 on the final, so it's a little bit less involved. But we want to, again, remember how to do this. We want to balance the redox reaction, and in problems like this, all you're ever going to have to do is supply the coefficients and then answer some question about those coefficients. We're not going to ask you to predict reactants or products. We're not going to do anything with acidic or basic solution, as some of you are already a little bit familiar with. We're just going to give you all the reactants and products. You just have to supply the numerical coefficients. So as you'll recall, the way that we want to approach this, because we need to make sure that both the atoms and the charges are balanced, the reliable way of doing that is using the oxidation number method, where we're going to assign the oxidation number of each atom and then figure out from there how many electrons are transferred first. And so let's go through all those steps. So in HNO2, the first reactant, it's a covalent compound, so hydrogen and oxygen are going to be +1 and -2, as they typically always are in covalent compounds. The nitrogen then is going to be, we have 2 -2s and a +1, which is -3, so nitrogen has to be +3 to balance it out. Remember that the sum of the oxidation numbers equals the charge of the ion or compound. This is a neutral compound, so all those oxidation numbers should add up to 0. 2 -2s, 1 +1, and then a +3. Okay, so those are the oxidation numbers for the first one. The second one is very easy. It's just H+ by itself, so any ion by itself is just going to have an oxidation number that's equal to its charge, in this case +1. Cr2O7 2-, very commonly occurring in redox equations, not the easiest one to find oxidation numbers for, but we have, again, oxygen, which is going to always be -2. So 7 -2s is -14. The sum needs to be -2 to add up to the charge, and so that means each chromium should be +6. 2 +6s is +12. 7 -4s is -14. Those added together gives you the charge. All right, so I'm going through the assignment of these oxidation numbers quickly, so if you need me to slow down, please let me know. But this is something that we should get pretty proficient at to be able to do these problems very well. NO3- now, we have oxygen still -2, but now with 3 of those, it's -6. The sum should be -1, so it's going to be +5 for nitrogen. An ion by itself, so just the charge, which is +3 for the oxidation number. And then water, one that we see all the time in these problems, -2 for oxygen, +1 for each hydrogen to balance out. Okay, so those are all the oxidation numbers. The next step is to figure out which ones are changing, to figure out how many electrons are being transferred. So we have a +3 on nitrogen on the reactant side, +5 on the product side. So these ones are changing. And then chromium is going to go from +6 to +3. So those ones are also changing. So then when we count electrons, that's going to be given by the difference in oxidation numbers. All right, so we're going to have, for nitrogen, +3 to +5, that's a difference of 2. Technically, it's losing 2 electrons because the oxidation number is getting larger, although we don't need to necessarily think about whether they're lost or gained to balance the equation. We just need to know what they are. So 2 electrons for that one. This one we have to be a little bit more careful about counting, because chromium is going from +6 to +3. So that's 3 electrons per chromium, but remember that Cr2O7 has 2 chromiums in it, so each of those is going to go from +6 to +3. So to remind ourselves of that, I'm going to put a 2 here, because whatever the coefficient is on chromium needs to be double on the product side versus this reactant to make sure that we have the same number of chromium atoms on each side. And that means when we're counting electrons, it's 3 electrons per chromium atom, but there's 2 of them that are involved. That's a total of 6 electrons. Because it's +6 to +3, there's 3 electrons each, but there's 2 of them that are changing by that amount, so it's a total of 6. So we have 6 electrons in this part, 2 electrons here. We need to make sure that they balance up. And so the way that we do that is we want to find the least common multiple of 6 and 2, and we can do that by just multiplying 2 by 3. And then what that means is that HNO2 and NO3- are both going to get coefficients of 3 to balance out the number of electrons. So then piecing that together, we have a coefficient of 3 in front of HNO2. We'll balance H+ last. And then the coefficients for dichromate, Cr2O7 2-, and then the chromium 3 are going to be now fixed at 1. And this one's going to have a coefficient of 3 also. And then Cr3+, we're going to keep that as a coefficient of 2. And then water, which we'll balance as one of our last things. And then the last step to completely balancing this is to balance water and H+. So we see that on the reactant side, we have a total of 6 plus 7, which is 13 oxygens. On the product side right now, we have 9 from nitrate. We don't want to change that coefficient, so we need 4 more oxygens from water, so that we now have 13 oxygens on each side. And then we have, on the product side now, we have 8 hydrogens. We have only 3 from HNO2, so we need to add a 5 in front of H+, and that should take care of all the balancing. And then what this one asked for was the sum of the coefficients, and so we have to just add up all these coefficients. 3 for HNO2, 5 for H+, coefficient of 1 for this, which is implied if it's not written. And then on the product side, 3 for NO3-, 2 for chromium 3+, and 4 for water, which all add up together to be 18. Okay, so that's how we do that one. We had a couple questions pop in, so let me see what they are. So the question was, we have, how did the element chromium get +6, and why is it 3 NO3-? So to answer both of those questions, to get +6 for chromium in the reactant side here, so it's a little bit of an algebra problem in some sense. So Cr2O7 2-. So in any compound or any polyatomic ion, oxygen is going to be 2-. So we have 7 -2s from oxygen. So each oxygen is -2. We have 2 chromiums in the formula, so we're going to assign the oxidation number of that. And the sum of these has to equal the charge of the ion, which is -2. Okay, so if we have -14 from oxygen, we need to have then +12 from the chromiums in total to add up to -2, but there's 2 chromiums, so it's going to be 2 times +6. So in any polyatomic ion like dichromate, the sum of the oxidation numbers equals the overall charge. So oxygen, chromium, and then this is your overall charge. All right, so it's 7 -2s from oxygens, plus 2 plus 6 from chromium will give us the overall charge of -2. So we're sort of working a little bit backwards and getting chromium last from that. The second question was, why is it 3 in front of NO3-? And that's because the 2 species that are involved in this redox change are HNO2 and NO3-. And so if the oxidation number here is changing from +3 to +5, that's a 2 electron change. As we said, we have to triple that to make it equal number of electrons, 6 for this and 6 for there. And then that means we have to triple both coefficients. So whichever species are connected by the tie line, meaning that they have one of their atoms that's changing its oxidation numbers, whatever you do to one coefficient on the left side, you have to do the same thing on the right. So if we add a coefficient of 3 in front of HNO2, we also add a coefficient of 3 in front of NO3-, and that now means that we have, for this part of the reaction here, a total of 6 electrons. Okay, so hopefully that makes a little bit more sense now that I clarified it. Any other questions on this problem? Looks like nothing coming in, so I'll go ahead and move forward. All right, so we are already now, believe it or not, into the last part of the course, the chapter 7, 8, 9, which you just had an exam on, so this should hopefully be pretty fresh in most of your mind. So I think this does give you a bit of an idea that chapters 5 and 6 are not particularly heavily emphasized on this exam. I don't think there's a particular rhyme or reason for that. That's just how it is. So only a few questions dealing with chapters 5 and 6, stoichiometry, solutions, all that stuff. Now around to the end, the last 10 questions are going to deal with chapter 7, 8, and 9, which is heat, work, gases, and all the stuff that we've done most recently. So the first question here, we have a sample of gas absorbs 125 kilojoules of heat and then performs 12.6 kilocalories of work. What is the change in internal energy delta E? So for problems like this, if we're telling you about heat and work and asking you to calculate delta E, you should immediately zone in on this relatively simple equation here. The change in internal energy for the system is equal to the sum of heat, which is Q, work, which is W. All right, so that's what we're going to be using. And those are really the only 2 ways that the energy can change, is either by the system absorbing or releasing heat, or having the system do work or have work done on it. Those are the only 2 forms of energy transfer you can have. And so if we know both of these numbers, we can calculate delta E. Now, there's 2 tricky parts to these problems. One is that we don't usually directly give you the sign for Q and W. You have to, that's going to be implied based on the wording in the problem. And secondly, we have to make sure the two numbers are in the same units before we can add them together. So if we look at the heat term first, Q, we have 125 kilojoules. And the key word here is it absorbs that much. So if you have, basically for Q, you can either absorb or release heat. If it absorbs heat, that's going to be a positive Q. If it releases heat to the surroundings, that's going to be negative. So this is absorbing heat, which means that Q is going to be plus 125 kilojoules. And then if we go to the W part, work is going to be, the magnitude of that is going to be 12.6 kilocalories, but we need to make sure we get the sign correct. So if work is done by the system or performed, that's going to be a negative number. And if work is done on the system, then it's going to be a positive W. So in this case, it says the system performs 12.6 kilocalories of work, meaning the system is doing work on the surroundings. The work is done by the system, so this should be a negative number. Now, the other thing we have to do before we add them together is get them in the same units. We want delta E in kilojoules, so that means the work needs to be converted to kilojoules. So the work is minus 12.6 kilocalories, and then the conversion factor from calories to joules is the familiar number 4.184. which is also the specific heat of water. So 4.184 kilojoules in 1 kilocalorie. All right, so give me just a quick second to get that because I forgot to do this one ahead of time. All right, so what we get is 52.7 kilojoules, still with the minus sign out front. And then finally, we can add these two numbers together. We have Q, which is plus 125, W, which is minus 52.7, and the sum of those is going to give us delta E. So we have 125 kilojoules, that's Q, plus negative 52.7 kilojoules for W. And so what we end up with, 125 and then negative 52.7 is 72.3 kilojoules positive. Now this is technically too many significant digits, I suppose. It should be just 0 decimal places, but in a problem like this, we would specify the answer format, so don't worry about significant figures too much. All right, so that's how we do it. It's just Q plus W. We have to make sure, though, that we get the correct sign for Q and W as well as the correct units before we add them together. So any questions on that? All right, let's keep going then. Oh, we did have one just come in, so let me take that before I move on. So there is a question. So I'll give you, we'll wait just a second for it to come in. So isn't the 4.184 conversion factor joules per calorie? Yes, it is, but it can also be kilojoules per kilocalorie. If you put the same prefix out in front of both of them, kilo, you can still use the same conversion factor. So it would be 4.184 joules in 1 calorie. That's sort of the standard form of the conversion factor. But if we multiply the top and the bottom, the numerator and the denominator by 1,000, that's equivalent to 4.184 kilojoules per 1 kilocalorie. So if you have these compound units, you can add the prefixes. As long as you add the same prefix to the top and bottom, the conversion factor will be unchanged. All right, on to 26 then. So this is, we're going to, in this problem, calculate delta H for a reaction, and we're giving you 3 equations with known delta H values. So this is going to be a typical Hess's law problem where we have to figure out how to combine these 3 equations that are given, modifying them as necessary to be able to produce this as our overall chemical equation. So the way we're going to do that is if we look at this, this problem here, we have CH4, NH3, this is the equation, goes to HCN and 3H2. So if we look at the reactant side, we have CH4, and we're going to find out where that appears down here in the given equation. So CH4 appears in equation 2 here, but it's on the product side. So to get CH4 on the reactant side, we need to flip equation 2. So that's going to be the equivalent of taking the negative of equation 2. And so we're going to flip that one. We can do these in any order, but I'm just going to go from reactants to products in the overall equation. So if we flip equation 2, we get CH4 goes to C plus 2H2. I'll leave out the states of matter. Those aren't going to be terribly important in this case for balancing. And then if we flip the equation, then we have to also change the sign of delta H. So the delta H for this modified goes from negative 74.9 to positive 74.9 kilojoules. All right, so we flipped the sign, we flipped the order of this equation, so that means we flipped the sign of delta H. So that gives us CH4 on the reactant side. The next reactant that we need is NH3, and we'll see that NH3 appears in equation 1 that's given to us down here, but it appears again on the product side and with a coefficient of 2. So what we're going to do is we're going to flip equation 1 and we're going to multiply all the coefficients by 1/2 so that this coefficient of 2 becomes a coefficient of 1 as it's supposed to be in the reaction that we're going to calculate delta H for. So we're going to take minus 1/2 times the first equation, which again is equivalent to flipping it and multiplying the coefficients by 1/2. So instead of 2 NH3 on the product side, we just have 1 NH3 as a reactant. And then these two reactants become products with their coefficients modified by 1/2. So NH3 going to 1/2 N2 and then 3/2 H2. In the delta H for this modified equation, we flip the equation and we multiply coefficients by 1/2, so we change the sign and multiply the whole thing by 1/2. So this number here, minus 91.8, is going to be multiplied by minus 1/2 to give us a positive number once again of 45.9. All right, and so that should take care of having CH4 and NH3 on the reactant side, which we need. If we go to the product side, we have HCN and H2, so we could potentially use either of those to figure out what to do with this third equation. However, we notice that H2 appears in all three of the given equations, so it's not going to be as straightforward to figure out how to balance H2, so let's look at HCN. HCN appears here as a product on equation 3, but it has a coefficient of 2 instead of a coefficient of 1. So we don't need to flip equation 3 because HCN is already on the correct side of the arrow, the product side, but the coefficients are still off by 1/2. So we're going to take 1/2 and multiply equation 3 by a factor of 1/2, and that's going to give us 1/2 H2 plus C goes to, sorry, there's one more, 1/2 N2 goes to HCN. Then the delta H for this, we just multiply the coefficients by 1/2, so we're going to just multiply the whole delta H by 1/2 for the third equation, not changing the sign in this case because we didn't change the order of the reactants and products. So we multiply that by 1/2 and we get 135.2 thereabouts kilojoules. All right, so those are the three modified equations. If we trusted ourselves to do this correctly, at this point, we can just add the three numbers together, but it is good to check that the three modified equations do add up to give this one here, which is what we're looking for. So let's go and make sure that it does that. So CH4 carries forward as a reactant. So we're going to add up everything on the reactant side and everything on the product side and combine them and see if it works out. So CH4 carries through NH3. If we go to H2, it's more complicated though. So we have half H2 on this reactant side, but then H2 also appears in two of the other equations on the product side. So basically this half H2 is going to cancel out. If we subtract half an H2 from this one and then subtract half an H2 from that one, they would partially cancel out. And then the carbon here that's on the reactant side cancels out with that carbon that's on the product side. And then 1/2 N2 reactant side here cancels out with 1/2 N2. So the only thing that's left on the reactant side is CH4 and NH3 as it should be. And then on the product side, we have HCN that carries through, and then hydrogen, we have two H2s here, one H2 that was left here when we partially canceled out the 1/2 H2 on the other side, and so we still are left in net with 3 H2s as we should. So it is good to double check that everything adds up correctly, and then we can be sure now that we can add up the 3 delta H values to get our overall delta H. So it's just going to be these three numbers added together, 74.9 kilojoules, 45.9 kilojoules, and 135.2 kilojoules for a sum of 256.0. This one just wanted the number with one decimal place in no units. We would just enter 256.0 for that one. All right, so those problems are a little bit tedious. It's going to be one of the more time-consuming types of problems you likely have to do, but if you trust the method, and we've done enough practice problems on this by now, hopefully it's getting more routine for everybody. So do we have any questions on this one? All right, let's move on then. Make sure we don't keep everybody here too long. All right, we did have one come in, sorry. Let me get to that before I get to the new question. Why it didn't add up 4 equations? I'm not sure I'm 100% following what you're asking, but if you're asking why we didn't add up all 4 of these equations, you're talking about this one plus all 3 of these. The reason is that this is the equation we're trying to find. So what we want to do is we want to figure out how to add up these 3 equations to get this one here. So this matches, these two match each other, so we know that we did it correctly. So we're only going to add up the 3 equations that are given to us with the included delta H values. We're not going to add up the other one with those. We're actually trying to find what the delta H for this is. That's sort of the whole point of this problem. So if that was what you're asking, hopefully that answers it. Anything else I can clarify? All right. If that didn't answer your question, please leave another message and I'll get back to it in a little bit, but let's move on for now. So we have a container of gas with a movable piston. It has a volume of 123 milliliters when the pressure is 562 torr and the temperature is 25 degrees Celsius. What will the volume read if the pressure is lowered to 253 torr and the temperature is raised to 97 Celsius? So this is a pretty typical ideal gas problem where we have a sample of a gas and we're giving you 2 different conditions of temperature, pressure, and volume, and asking you how one of those is changing in response to the others. So in any problem like this, you want to start with the ideal gas equation, PV equals nRT. Instead of memorizing a bunch of individual relationships between pressure, volume, number of moles, and temperature, we can always derive the one that we need. So in this problem here, we're told that the volume is changing because it starts at 123 and we're trying to find out what it is. The pressure is changing from 562 to 253 torr, and the temperature is changing from 25 to 97 Celsius. So basically, pressure, volume, and temperature are all changing. We didn't tell you about the number of moles, and we're assuming it's a closed container, one that's not leaking, so we're not going to do anything with number of moles. So what we're going to do is we're going to take the 3 variables that are changing and move them over to one side of the equation. So pressure over volume divided by temperature is equal to NR, and that ratio has to be constant. And so then the equation we're going to use is P1V1 over T1 equals P2V2 over T2. This is sometimes referred to as the combined gas equation because it's basically Boyle's law and Charles's law sort of blended together, although we don't need to necessarily know that's what it's called or even memorize this equation because it can always be formulated from PV equals nRT by just taking all of the variables that are changing and moving them over to one side. All right, so what we're looking for in this problem is the final volume V2 when we change the pressure and the temperature. So we're going to solve for V2 or V1 depending on how you define each one. And so that's going to be, let me write it in a more convenient way. So V2 is going to be V1 times the ratio P1 over P2 times the ratio T2 over T1. All right, so those are going to be the numbers that we need to be able to figure out what V2 is. So now we have all the numbers, all these are given to us. We just need to make sure we put them in and make sure that the units are okay. So V1 is 123 milliliters. We can use whatever volume we want for pressure and volume because there's no universal gas constant in this equation. So pressure and volume can be whatever we want. So we're going to have 123 milliliters for V1, and then the two pressures, P1 over P2, can also be whatever units we want as long as they're the same as each other so that the units divide out. So P1 is initially 562 torr, and then P2, the final pressure, is 253. So those are the two pressure values in the correct order. And then we just need the ratio of T2 over T1. But no matter what type of problem we're doing, the temperatures do need to be in Kelvin. So T1 is 25 degrees Celsius. We add 273 to get it to Kelvin. And then T2 is 97 Celsius. And we're going to again add 273 to that to get it into Kelvin 370. All right, so we do need to make sure the temperatures are always in Kelvin for problems like this, whenever it's just T given, absolute temperature, not any change in temperature. So that's going to be 370 Kelvin for T2 over 298 for T1. All right, so forgetting to convert temperature units is one of the more common mistakes in these. And what we should end up with is 339 milliliters. I guess this asks for 1 decimal place, and I didn't calculate it out that far, so but Blackboard's not that picky as long as your answer is close. Just follow the instructions to make sure that you're not rounding too much. So 339 would be the answer. Technically, we should put 1 decimal place in to make Blackboard happy, but as long as you're close enough, it's fine. All right, so any questions on this problem? All right, so there's a whole lot of variations on this, of course, depending on which variables we're changing, which ones we're not changing, but that's sort of the typical approach we'll take. And then 28 deals with gas density. So with gas density, if we give you the mass of a gas, or we're asking you something about, we're asking you something about the mass of a gas in a certain volume, we can basically rewrite PV equals nRT to deal with the mass. Remember that density is defined as mass divided by volume. And so what we can do for problems that involve density or problems that involve masses of a gas in more general terms is we can take PV equals nRT as our starting point, which is always going to be true for ideal gas calculations. But then we can rewrite N, which is the number of moles, as mass divided by molar mass. So remember that this is the relationship we use all the time for moles in doing stoichiometry problems. The number of moles is the mass of a substance divided by its molar mass. And so we can basically rewrite the ideal gas equation by taking this and putting it in for N. So we can say that PV is equal to mass divided by molar mass times RT. And then since we're calculating density here, this is mass divided by volume. And so we just rearrange this whole equation, putting mass over volume on one side. So we divide both sides by V, we cross multiply and divide by M molecular weight and RT, and what we end up with is that the density is equal to pressure times molar mass divided by RT. Now, if you want to, commit mental bandwidth to memorizing this equation, or if you want to put it on your cheat sheet, that's perfectly fine. That density is pressure times molar mass over RT, but like I said, it comes straight from the ideal gas equation, so if you forget it, you can still get to it like I did, showing you here. All right, so now we're ready to do the problem. And the other thing that we need to know is that anytime we tell you that we're at STP, that means standard temperature and pressure, tells us that the pressure is 1 atmosphere and the temperature is 273 Kelvin, or 0 Celsius if you like Celsius. So we can now calculate the density. Density is equal to 1 atmosphere, that's the pressure, times the molar mass. The molar mass of SO2, I'm not going to calculate it out in detail, but it's going to be 64.07 grams per mole. And then in the denominator, we have RT to calculate density. So R is the universal gas constant, 0.0821. Because we're using R in this calculation, the pressure does need to be in atmospheres. So those cancel out. And then we need to have the temperature here in Kelvin in the denominator, which for SCP is 273 K. And so what we end up with, we want 3 decimal places in this, is going to be 2.858. Paying close attention to units, so moles cancel and kelvins cancel, it's going to be grams per liter. So when you calculate the density of a gas in this way, the unit is grams per liter, not grams per milliliter, which is more conventional for liquids and solids. So that's the answer that we get there. There is another way of doing this, but I guess I can show it quickly. Another shortcut is that if you're at STP, 1 mole is equal to 22.4 liters for any gas. And so what you can do is you can say that we have a molar mass of 64.07 grams in 1 mole, and then multiply that by this conversion factor. 1 mole has a volume of 22.4 liters. And so moles cancel, and you would also get grams per liter that way. So that is a little bit of a shortcut. Just don't abuse that shortcut because it's only going to be true at STP, standard temperature and pressure. This equation here works under any conditions of temperature and pressure. And it will give you the same answer whether you use this equation or in this problem where it's okay to do it, you can use this shortcut that 1 mole of gas has a volume of 22.4 liters. And just do dimensional analysis to go from grams per mole to grams per liter. But like I said, the shortcut's a little bit of a danger zone at times because it only works at STP. You don't want to use it any other time besides that. Okay, so do we have any questions on this problem or the concept of gas density? All right, if not, let's keep going. All right, this problem here deals with effusion. So we have a 1.5 mole sample of CO2. It effuses in 13.3 minutes. How long would it take a sample of iodine vapor to effuse under the same conditions? So in these problems, one of the difficulties is getting the equation right. There's really only one equation for Graham's law when we're dealing with effusion or diffusion and how fast it takes or how long it takes to do that, but there's sort of 2 variations of the same equation depending on whether we're talking about the time that it takes to effuse or the rate at which it effuses. So in this problem here, though, we're dealing with CO2, and the equations that we're dealing with, as we'll show here in a second, involve molar masses. So the molar mass of CO2 is 44.02 grams per mole. And then iodine, which you have to recall is I2. The standard state for iodine is I2, and the molar mass for that is going to be 2 times the atomic mass, which is 253.8. So the atomic mass of iodine from the periodic table, double that to get 253.8 grams per mole. So before we set up the equation, before we get an answer, it's helpful to think about this a little bit conceptually because the key concept of, or one of the key concepts of the kinetic molecular theory of gases is that if you have 2 gases at the same temperature, the gas that is lighter is going to be moving faster and the gas that's heavier is going to be moving slower. And so if CO2 is a much lighter gas than I2, that means it's going to move faster or it's going to effuse faster. So if the time that it takes for CO2 is 13.3 minutes, the time that it takes for I2, which is heavier, should be longer than that. If it's a slower moving gas, it should take a longer time to effuse or leak under those same conditions. And so that means when we set up the equation in terms of time, it's going to be directly related to the molar mass. The time for I2 divided by the time for CO2 should be the square root of the ratio of their molar masses, directly related. So molar mass of I2 divided by molar mass of CO2. All right? So because I2 is heavier, it should take a longer time, and then that means the molar mass and the amount of time that it takes are going to be directly related to each other. If we're dealing with rate of effusion, you'd have to flip one side of this equation for it to work, but here we're dealing with the amount of time that it takes. All right? So then what we can do is start putting in the numbers. So the time that it takes I2 to effuse is our unknown. We're told that it takes CO2 13.3 minutes. And then that's going to be equal to the square root of the molar mass ratio. So I2 we calculated as 253.8. And then CO2 is 44.02. So we just divide the two, take the square root, and then cross multiply. And we get that the time that it takes for I2 to effuse is going to be 31.9 minutes. All right. And as we said at the beginning, it should be a larger number than for CO2 because it's a slower moving gas. So if we didn't get a larger number, that would suggest to us that this side or one of the sides of the equations was written in the wrong order. All right, so I had a question roll in. The question was, does it matter what element we put in the top or bottom? And the answer to that is no. So we could have just as easily set this up as the time for CO2 divided by time for I2 is equal to the square roots of the molar mass for CO2 divided by the molar mass for I2. You'd have to flip both sides of the equation for it to still work. In other words, the time is still directly related. So if the time for one is in the numerator on one side, its molar mass would be in the numerator on the other side. But it would work either way. The algebra would probably be slightly more challenging for this one, I suppose, but it still would work out if you're able to do it correctly. So it doesn't matter what order you put them in. I set it up this way to make the algebra convenient, but either way will give you the same answer and the right answer. So the next question that came in is, does the 1.5 mole of CO2 not matter? So no, in this problem it doesn't. So for Graham's law, for anything dealing with effusion or diffusion, all that matters is the molar mass. So all we're saying with 1.5 moles is that 1.5 moles effuses in 13.3 minutes, and then it didn't really specify it in these exact words, but then we're asking how long would it take 1.5 moles of iodine to effuse under the same conditions. Now, if you really wanted to, it would be more work. We could say that for CO2, the rate is 1.5 moles over 13.3 minutes, and we could have used the equation for rate instead of time, but I think it's easier to just start with time directly and not have to calculate a rate and then work backwards and get time again. It's just a lot of extra steps. So you don't need to know how many moles are effusing or diffusing. That is completely extra information in this problem. And so all that matters is that the two gases are at the same temperature, and if that's true, and if you're studying them under the same conditions, this is really the only equation you're ever going to have to use for Graham's law, whether we're talking about diffusion or effusion. All right, I think we had another question that came in was, is it better to cross multiply? I mean, that's what we're doing, I think, right? So you had, if we want to do the algebra for this one, I don't have all the numbers written out, but basically you would just cross multiply by 13.3 to move the 13.3 over. So the time for I2 would be this square root ratio, whatever that is. I didn't calculate that out exactly in my notes. I don't have that number in front of me, but you take the ratio of the square roots of the molar masses. Keep in mind the whole thing is under the square root sign if it's not obvious from how I wrote it. And then you're going to multiply that by 13.3 minutes. So it is cross multiplying. However you set up the equation, you're going to have to do some form of cross multiplying to solve for whatever your unknown is. In this case, the time it takes for I2 to diffuse. All right. All right, and then finally we're ready to get into the ending parts, which are just going to be 5 questions with chapter 9, the most recent stuff. And there's really not a lot of new stuff that you guys have to worry about. That's new, that wasn't tested already. So chapter 9 is the most recent stuff. Most of the topics from chapter 9 that we still included in this course we're going to already be tested on to some extent on the last exam. There's just one new topic, the very last question on phase diagrams. But we'll go ahead and go through these anyway because there are some differences in how they're set up, and we can review some of the key topics. So one of the key topics in chapter 9 was intermolecular forces and different types of substances, and those are the concepts that are dealt with in this question here. So we want to know which of the following elements in their standard states are the atoms or molecules held together exclusively by London dispersion force. So that means that's the only force that's holding together the atoms or the molecules. Okay, so if we go look at choice A here, we have to think about the standard state for each element. The standard state for carbon is graphite, and both common forms of carbon, graphite and diamond, are classified as network atomic solids, or network covalent solids more specifically. And what that means is that in both forms of carbon, the atoms are held together in their standard state by covalent bonds. Okay, so you have a large network of covalent bonds that's holding all the atoms together. So you don't just have London dispersion forces holding together, you also have covalent bonds that hold all the atoms together. Choice B here, sodium is a metal. I always forget to give you the symbol for gold. I assume everybody's as obsessed with gold as I am. Choices B and C are both metals. So let me write out both of those. All right, so sodium is a metal, gold, Au. We'll go to the periodic table quickly and find those. Sodium is one of the main group metals. Au is a transition metal. So both of those answer choices are metals, and that means they're both going to have metallic bonds holding the atoms together. Okay, so for choices B and C, you're going to have metallic bonds. So you're not going to only have London dispersion forces, you're going to have metallic bonds holding the atoms together. And then finally, for choice D, we have to think about the standard state for sulfur, which is S8. It is a solid in its standard state as well. And basically, it's going to be consisting of molecules of S8, so it's a molecular solid. And those molecules are going to be nonpolar because they're all the same atom involved. And if you have a nonpolar molecular solid, that means the only intermolecular force you have is London dispersion forces. You do have covalent bonds holding the individual molecules together, but then the collection of molecules that's in the solid are not going to have any other forces besides London dispersion. So the correct answer for this would be sulfur, which is choice D. And that's going to be the one that has exclusively London dispersion forces holding its molecules together. The rest of these are going to involve some sort of covalent or metallic bonding in addition to other types of forces. Okay? So do we have any questions on this topic? All right. 31 deals with a topic we didn't spend a lot of time on in class, but one that there's a possibility of getting a question about on the exam, which is semiconductors and band gaps and band structures. All right, so we want to know for which of the following statements is false. All right, and so the concept here that we're dealing with is what's called band gap. And what it means is that we talked about molecular orbital diagrams at the very beginning of this. So molecular orbital diagrams where you take all the atomic orbitals and you mix them together and make bonding and anti-bonding orbitals. And then in extended solids, metals, semiconductors, other solids that are, that exist in our world, there's also going to be sort of a molecular orbital diagram, but they're going to be represented as bands because you have a lot of molecular orbitals that are all going to be very close together. So you get basically a band of orbitals, often a gap between them, and then another band of orbitals. So the lower set of orbitals are going to be filled, and we call this the valence band. The upper set of orbitals are going to be unfilled. We call that the conduction band. And the energy gap between them, this vertical scale being energy, this gap between them is what we call the band gap. And what's going to determine whether something is a metal, a semiconductor, or an insulator, a conductor, a semiconductor, or an insulator, is going to be how large this band gap is. Conductors basically have no band gap, meaning that the two bands are right on top of each other. Semiconductors have sort of intermediate band gaps. There's a little bit of a gap there, but there's enough energy for electrons to move between the two. And then insulators are going to have a large band gap such that the electrons in the valence band are not able to go to the conduction band at all. So if we look then at the answer choices here, the first one is going to deal with the concept of band gap. Silicon has a larger band gap than aluminum. So in the periodic table, we can see that aluminum and silicon are right next to each other. But in terms of their classification, aluminum is a metal, which means that it conducts electricity. But silicon is one of our metalloids, one of those borderline elements. See, these are both right along that imaginary staircase. But aluminum is to the left and it's classified as a metal. It's a conductor. Silicon, just on the other side of that, is a semiconductor. It's a metalloid. Okay, so if we have silicon, which is classified as a semiconductor, and aluminum, which is classified as a metal, we would expect that the band gap for silicon would be larger than aluminum. Semiconductors have larger band gaps than metals or conductors, and so the first statement is true. The second statement here deals with the doping of a semiconductor. So in addition to silicon just being what's called an intrinsic semiconductor, you can also put in small amounts of other elements, and that will change the semiconducting behavior. So if we dope silicon with phosphorus, would this be a p-type semiconductor? That's what this statement is asking us. So to figure out if it's p-type or n-type, you look at the number of valence electrons, both for the main element, silicon, and for what we're doping it with, which is phosphorus. So in the periodic table, silicon has 4 valence electrons because it's in group 4. And then if we dope it with phosphorus, phosphorus has 5 valence electrons because it's in group 5. So in this situation here, where silicon has 4 valence electrons and the dopant phosphorus has 5, if the dopant has more valence electrons than the main material, we call that p-type. Sorry, we call that n-type. God, I mixed it up already in my head. This is n-type. Whenever you have more valence electrons in the dopant and you're putting extra electrons in, that's n-type behavior. So this one would be false. Keeping track of them up here as well, because this type of doping would be n-type, not p-type. All right, so that one's wrong. And then finally, for answer choice 3 here, the conductivity of silicon increases with temperature. So another distinction between semiconductors and conductors or metals is how their conductivity changes with temperature. So in any semiconductor, the conductivity will increase when the temperature increases. All right, so whether it's silicon or any other semiconducting material, if you increase the temperature, you increase the conductivity, and that's because at higher temperature, more of the electrons in the valence band have enough energy to jump up to the conduction band, which is what causes conductivity. So that's true for any semiconductor, so this one would also be true. For metals, anything that's classified as a conductor, that's a metallic substance, in that case, the conductivity will decrease when the temperature increases. So that's another distinction between metals and semiconductors, is how the conductivity changes with temperatures. This would be true for a semiconductor, but for a metal, it would be the opposite. The conductivity would decrease when you raise the temperature. So the only false statement in this set of 3 is going to be the second one. So the correct answer for this would be B, that number 2 is the only false statement. All right, any questions on that topic? I don't think I missed any. So if not, let's move on to 32. All right, so number 32 is, what is the empirical formula of a compound that contains A on the corners of a cubic lattice, B on the edges of the cubic lattice, and C in the center? Now, technically, we skipped the topic of ionic compounds, which is kind of what this is related to, but this particular problem here only requires that we know how to count the atoms that are on the different positions of the cubic unit cell, which we did cover and which we do expect you to know. So we have 3 different elements in this cubic unit cell, abbreviated generically as A, B, and C, and we want to know what's the formula given the arrangement that's stated in this problem. All right, so if we have A on the corners of the cubic lattice, remember that there's 8 corner positions in total, and then each of those is going to count for that unit cell as 1/8 because they're shared by by a total of 8 unit cells. So these are the corner atoms, 8 of them total, each counting as 1/8. So in net, we have 1A in the unit cell. For B, we have B on the edges of the cubic lattice. In a cube, you have 12 total edges. Each of those edges would be shared by 4 unit cells. So each one of those is going to count as 1/4 belonging to that specific unit cell. And so 12 times a fourth is 3. So we'd have a total of 3 Bs in the unit cell. And then if we have C in the center of the cubic unit cell, there's just one center position, and it's completely inside the cubic unit cell, so it's not shared at all, counts as 1 full atom. So there's also 1 atom of C. And so that means the empirical formula for this compound, we'd have 1A, 3 Bs, and 1 C. AB3C would be the empirical formula for this specific compound where the atoms are arranged in this way. All right. So there are going to be several questions within the problem bank that involve just how to count the different positions in a cubic unit cell. So make sure we know that this is what we have for corners, this is edges, This is the center. The other one that we didn't cover in this one was the faces, which count as 1/2 each. And there's 6 total faces. All right, so we didn't have any face positions occupied in this problem, but this would be the other potential alternative. If we had atoms on the faces of the unit cell, there's 6 total faces, each one shared by 2, counting as 1/2. So does anybody have any questions on cubic unit cells, or and specifically how to count the atoms in a cubic unit cell, which is probably the most important thing you'll have to do for this test? Okay. And then number 33 is another question dealing with classification of solids. And so with classifications of solids, there is one slide in the very beginning of the last lecture notes that summarizes this. And so definitely go over that and review that if you need to. So there's different categories. There's metallic solids, ionic solids, molecular solids, network solids, all different, a few different categories that we're going to be aware of. And what's going to determine those classifications is mainly going to just be the type of elements that makes them up. All right, so if we go to these answer choices here, if we have I2, which is a covalent molecule, if you have a substance that's made up of molecules, it's going to be classified as a molecular solid, which is what the problem is looking for. So any substance, if you have a molecular compound, a covalent compound that's made up of molecules, if you cool it down so that it's a solid, that solid will be classified as a molecular solid. So I2 would be a molecular solid because you have molecules of I2, and they're going to arrange themselves into a solid lattice, which is going to be held together just by London dispersion forces. In choice 2, which is water, if you cool water down into the solid, we call that ice, of course. And the formula for water is H2O. This is also a covalent molecular compound. In this case, the molecules will be held together not only by London dispersion forces, but also by hydrogen bonding interactions, because water has these polar OH bonds in it. But this would still be classified as a molecular solid. It's molecules of water arranging themselves into a lattice. So both of those first two are molecular solids. If we go to number 3 here, which is sodium, we already dealt with sodium in a recent problem. Sodium, which is Na, it's a metal, and any metal by itself, whether it's a main group metal or transition metal, a solid of that metal would be classified as a metallic solid, and that's one of the other major classifications. So this is not a molecular solid because it's not made up of molecules. Any metal would just be considered a metallic solid. Choice 4 is SiO2, and this is one that we're going to definitely have to remember, because if we go to the periodic table and look at where Si and O2 are, as we said, silicon is sort of here in between metals and nonmetals, although it is on the right side, so it's more like a nonmetal. Oxygen is a nonmetal, so you might be tempted to conclude that SiO2 is also a molecular solid because it's 2 nonmetals, which could potentially form molecules. But SiO2 is really the only example that we have of a network covalent solid where we have at least one that has 2 different types of elements in it. So this is a network covalent solid, SiO2. And it's the only type of that would involve 2 different elements, in this case silicon and oxygen. So the way SiO2 looks is that you don't have discrete SiO2 molecules, you have tetrahedral arrangements of silicon and oxygen, and then they're going to be in sort of these large networks with other silicons and oxygens all over the place in all directions. So I'm not going to draw much more of this, but that's sort of the idea. Silicon oxide SiO2 is an extended network covalent solid. It's not individual molecules of SiO2. And that's the classic example of a network covalent solid. And then finally, choice 5 here is NaCl. And we should recognize by now that NaCl is an ionic compound. It's a metal with a nonmetal. Any ionic compound would then be classified as an ionic solid, of course. So this covers most of the major categories: molecular, metallic, network covalent. There's also network atomic solids that are nonmetals. We talked about carbon earlier, so that's another major category that would sort of be of the same type but only have 1 type of atom, not 2 like SiO2 does. But the point of this problem is that these first 2 are the only 2 that are molecular, and so the correct answer for this would be B, that number 1 and number 2, I2 and water, are both classified as molecular solids. So do we have any questions on classifying solids or how I reasoned myself through this one? All right. And then finally, in number 34, the very last question, and the only one that deals with the new topic, which is phase diagrams. So in a phase diagram shown here, we want to know which of the following is correct. So the first thing to keep in mind with phase diagrams is it's helpful to divide these up into the different phases. So we're going to deal with relatively simple ones here, solid, liquid, and gas being the only three major phases. And so the solid is going to be all the way on the left, liquid in the middle, gas on the bottom right. So that's going to be the three major regions of this. And the lines that divide them are going to tell us what temperatures and pressures the phase changes occur between solid and liquid and between liquid and gas. And so let's go through the different answer choices here and figure out which one is correct. All right, so choice one, at 200 Kelvin and 1.2 atmospheres, only liquid is present. So if we look at the axis on this, we go to 200 Kelvin, which is our x-axis, 1.2 atmospheres, that point is up here, and you can see that that is in the middle liquid part of the diagram. And it's not on the line between any of the two phases, so only the liquid would be present at that pressure and temperature. So this one is correct. Choice two here, liquid can exist below 0.6 atmospheres. So if we draw a line straight across at 0.6 atmospheres, we see that the entire liquid region is above that. And that's because the triple point here, where all three of the phases intersect each other and coexist, that occurs at 0.6 atmospheres, and you can never have liquid below the below the triple point pressure. All right, so this is the triple point, and anything below that, you're only going to have solid and gas, so the liquid only exists above this pressure of 0.6 atmospheres. So that one's going to be false. And then in number three, moving from point C to point D in the diagram, the phase will change from liquid to solid. So here we're at point C, which is, we're starting as a liquid, so that part is true. But if we go to point D here, that's going to be in the gas part of the diagram, below the liquid gas line and to the right of the solid gas line. So this is going to go from liquid to gas, not liquid to solid. So this one is also going to be wrong, false. And then finally, point E for number four, point E is called the triple point. So E over here, which is where the liquid gas line appears to end, that's not called the triple point. The triple point is this one here where all three of them intersect. Where the liquid gas line ends is called the critical point, not the triple point. So that's wrong also. The critical point is basically where you no longer have separate liquid and gas phases. You just have what's called a supercritical fluid that is kind of in between a gas and liquid, if you want to think about it that way. So that point is called critical point, not triple point. So the only one of these that's correct is answer choice C, which is the one that states that a liquid is present at 200 Kelvin and 1.2 atmosphere. All right, so for this type of problem here, you just need to be comfortable with reading the different regions of a phase diagram and then understanding a little bit about the terminology related to phase changes. So solid to liquid is melting, liquid to solid is freezing, liquid to gas is called boiling or vaporization, gas to liquid is condensation. So a little bit about phase changes is going to be part of this, as well as just how to interpret these phase diagrams. All right, so we did have a question come in while I was going through this. Let's see what it is. So the question is, does that mean the liquid has to be above the triple point? And the answer is yes. So if you look at the pressure at which the triple point occurs, so this triple point is at a pressure of 0.6 atmospheres, the liquid will only exist at higher pressures than 0.6. Not at all temperatures, but the pressure has to be above 0.6 atmospheres for you to see the liquid. And that's true for any substance. So the triple point is going to be that boundary point there, and only at pressures higher than that are you going to ever see the liquid phase. All right, so does anybody else have any other questions on this? We have another one come in, so let me see what it is. The question is, what state would it be at point B? Let me remember where point B is on the diagram. So point B is the intersection between liquid and gas. So anytime you're on one of the lines, you would actually have both phases present. So if you're on the line that divides liquid from gas or any of the other two phases, you're going to have both of those phases present at that point in what's called equilibrium. We didn't really talk about equilibrium in any formal terms in this course, but what it basically means is that at those temperatures and pressures, when you're along the line, you'll have both liquid and gas present together at the same time. All right, other questions on phase diagrams or anything else that I covered today? All right, well, I hope that all of you are ready for your sprint to the finish. Hopefully not stumbling and being dragged across the finish line, but a nice healthy sprint to the finish line. And then, I wish you the best on the final. We did have one question come in more in general about the final exam. On the final exam, is it better to find some easy questions? I think in general in this course, that's a good test-taking strategy to look for the easy or especially the faster questions first, because keep in mind that, in this course, all of the questions count as 1 point, and it's all or nothing. There's no partial credit. So it's really in your best interest to make sure that you give yourself enough time to answer all the questions that you know how to do. So it doesn't really benefit you to spend 15 minutes pulling your hair out on one question if it's only worth 1 point. Move on to other questions that you know how to answer, and you'll be able to pick up more points that way. Also keep in mind that the final exam it's a little bit faster than the midterm. So the midterm was 20 questions, 75 minutes. The final exam is 34 questions, 100 minutes. So it's a little bit faster paced. But generally, we pick questions for the final that we hope don't take too long to do. You might disagree with us on some of those, but in general, we pick relatively straightforward questions that don't involve a lot of complicated steps, but you do need to know everything from this whole semester because it is a comprehensive exam. If there's no other questions, did the weight of the final change due to COVID? No. So we did not change the grading scale at all for this course. So we're still going to have the final exam and all the other exams be weighted the same. 2 bonus points available that we've been having throughout the semester, and also the same type of grading system that was in place at the beginning. The big difference that we have, which I think is helping at least some of you, is that you're able to use the cheat sheet on all these exams now. So hopefully you've been taking advantage of that. Hopefully that's helped you a little bit dealing with this new test-taking environment. But we don't have any plans to change the grading scale. It's a little bit late to do that at this point since we're so close to the end. All right, any other questions about the final exam, about any of the topics we covered? All right, if not, thank all of you for coming and taking the time to be here with me and for everything this semester. I had a great time teaching all of you. Unfortunately, our face-to-face interaction got cut short for circumstances out of our control, but for the most part, everyone's doing a great job of adjusting to the online teaching, still engaging as much as possible. So I certainly applaud your effort. I hope it translates into a good score on the final for everybody. And I'll be around all week if you have any questions you want to ask me related to your preparations for the final. So I have a pretty flexible schedule this week, so we can always set up times to either talk on this program, Microsoft Teams, or if you have questions you want to email to me, please do. And again, I hope everyone does well and has a great rest of the semester. And hopefully I'll be able to see you all again for real sometime. All right, so if there's no other questions, I'll sign off now, and I'll put this on YouTube for you guys later today. And have a good rest of your week.